Hello friends, so this is part 3 from the year 2024, and in this we are going to solve 4 questions from the advanced and 12 questions from the mains. So total we are going to solve 16 question, and this will be the last part of this year 2024. So first question, it states that two beads, each charge Q and mass M, are on a horizontal frictionless non-conducting circular hoop of radius r. One of the beads is glued to the hoop at some point, while other performs small oscillation about its equilibrium position along the hoop. The square of the angular frequency of the small oscillation is given by. So we can draw an approximate figure based on the given description. So we are having a circular hoop is there, and let's suppose this is our center, radius is our capital R. We are given two charge. Suppose the position of first charge is our P, that is our having Q and mass M, and this is the mean position, center is given as O, and the small displacement of the charge is, let us put this point, and it is given as Q. So Q is going to have second charge of mass M, and it is displaced from the mean position with the angle of phi. And if we join the center O with Q, you can say this angle will be also over phi, and the PQ is suppose denoted by a position vector R, and the radius vector OQ makes an angle of theta with the center. And we can just extend these two. So this angle will be also over phi. So, and this is the maximum displacement on the arc. Let us suppose this is given as x, and similarly small displacement on the other side will be also over x. And we can easily find out, or using the standard relation between the, because PQ is our chord vector, R is the radius, and our phi is the, you can say, angle through which it is moving in mean position. So we can write that our chord length R is equal to 2r and cos of phi. Okay. And the force between the two charges P and Q between the charges, let us suppose that is given as F, or let us suppose that it is dependent upon the phi, will be equal to K Q square and divided by our R square. And this is going to act along the same line. Okay. And one of its component will be acting as a restoring force, that is going to result in the oscillations. Okay. So we can just let me draw this point point Q. So this is point Q, and we are having force, that is F, and the angle is our phi. So this force we can divide into two components. One will be our this will be our F cos of phi, and other one will be our F sin of phi. So the storing force that will be acting is our F sin of phi. Therefore we can write that restoring force along the loop, along the hoop, sorry, restoring force along the hoop, let us call this Fr, which will be given as our F of phi, and we have this is sin of phi. We already know F of phi, so we substitute it, we get our restoring force Fr will be equal to K Q square upon R square, and we have this as sin of phi. And obviously there will be accelerated motion because of the restoring force. Therefore we can say that the acceleration of the bead along the hoop, acceleration of the bead along the hoop, let us call this as AR, and that will be equal to our restoring force divided by mass m. We substitute value the formula for the restoring force, we get that our AR will be equal to, and Fr is our K Q square m R square, and we have this sin of phi. Okay. So restoring, we can just put here the negative sign. We already know the expression for R. Substituting R, we get this as minus K Q square, and we have this m, and our R is 2R cos of phi whole square, and we this have our sin of phi. And we just open it, we get AR is equal to minus K Q square, we get this as 4m R square cos square phi, and multiply by sin of phi. But for small angular displacement, we can write that our sin of phi is approximately equal to phi, and our cos of phi is approximately equal to 1. Okay. This is because of the small oscillations, small angular displacement. So we substitute it, we get our A of R is equal to, this will be our minus KQ, and we have 4m R square, and multiply by phi. Okay. And we can define the relationship between the theta and phi. Theta is the exterior angle, so we can say our theta is equal to twice of phi. Okay, so from here you can write phi is equal to theta upon 2. And we can write that our AR is equal to minus KQ square, and this comes in now as 8 mr square multiplied by theta. And we also know that our restoring acceleration AR is nothing but our omega square times x. That is a standard relation. X is the displacement here, x is representation as a theta. So we can write that our omega square is asked here, so we get omega square is equal to KQ square, and we have this as 8mr square, and we can just substitute value of k. I think yes, so we can substitute it. That will be 1 upon 4 pi epsilon naught, so this comes as q square, and this is our 32 pi epsilon naught m r square. So this is our square of the angular frequency. And okay, 1 second, sorry, I made a mistake here. Yes, because x is our linear displacement along the arc and theta is the angle, so we can easily substitute our relationship between x and theta. So we can say our theta is equal to x upon r, and now it will be coming as cube. That was cube. And so we get this will be equal to our option number B is the correct one. Is correct. Next question. It states that a small electric dipole P naught having a moment of inertia I about its center is kept at a distance r from the center of a spherical shell of radius r. The surface charge density sigma is uniformly distributed on the spherical shell. The dipole is initially oriented at a small angle theta as shown in the figure. While staying at a distance r, the dipole is free to rotate about its center. If released from the rest, then which of the following statement is or are correct? So we are given a spherical shell of radius r, and sigma is the charge density on it uniformly, and we have a dipole at a distance of small r from the center, and the distance, this r, is center of the dipole. Initially it is released at a level theta with the vertical. Okay, so we have to find out various there are only two things to find out basically, and it says that the condition for the oscillations, these are first two, and the second two, last two, C and D, are with respect to the angular frequencies, okay, for various values of radii. radii and distance of the dipole from the center. So we are given this charge density. Let us suppose the total charge on this spherical shell is our capital Q. Okay. Therefore, we can write that total charge on the spherical shell which is given as Q. So this Q will be equal to our 4 pi r square and multiply by surface charge density. And so first of all, we are going to find out the electric field, because it is the dipole is going to experience a torque because of the electric field. So let's find out first of all the electric field. Let us call this as point as O and this point as O prime. And we know the relationship, or we can say formula for the electric field due to a spherical shell at any point outside. You can say electric field due to spherical shell at a distance r which basically means outside. We can write that our electric field E will be equal to K, charge is our Q, and divided by R square. We can substitute value of Q, which gives us K, and we have here 4 pi R square and multiply by sigma divided by small r square. Let me write the value of K, that is 1 upon 4 pi epsilon naught. So here 4 pi cancels out, so we get this as r square sigma divided by epsilon naught small r square, and this field will be radially outward. Radially outward. So let's find out the torque on the dipole. Torque on the dipole, and the torque, let us suppose given as tau, will be equal to dipole moment and the electric field. And one second. Okay, so direction of this is given, so obviously this end will be positive. One second, direction is given. Yes. So because of the electric field, so there will be two forces acting on it, so that will be resulting in a torque. And so we can say the torque will be equal to PE, and we have this as sine of theta, and for theta to be small, we can approximate it equal to PE times theta. Okay. And along with it is also mentioned that it is having a moment of inertia I about its center. So we can also write that our equation of motion which gives us that our torque will be also equal to our I multiplied by double derivative of the our displaced angle. So we can just substitute the equation, because this is restoring torque and this will be also our torque because of the moment of inertia. And here we can write our I double derivative of theta with respect to time is equal to, this will be minus PE times theta. We make some adjustment in it. We can write this as double derivative of theta t square plus PE divided by I multiplied by theta is equal to 0. And this is nothing but equation in the form of a quadratic, and which represent a standard SHM equation. So we can make a comparison of this equation with the standard one, theta upon t square plus omega square theta is equal to 0. So this 1:1 comparison gives us that the value of omega will be equal to, rather omega square will be equal to our dipole moment P divided by E. And we already know the equation for the electric field. So we substitute it, we get omega square is equal to, and dipole moment is given as P naught. So we substitute it as P naught divided by I, and we get this as R square sigma divided by epsilon naught R square. And from here we can say our omega is equal to square root, and we have P naught R square sigma I epsilon naught small r square. Okay, now let us check the options one by one. So first option states that the dipole will undergo small oscillation at any finite value of r. Okay, any finite value of r basically means that this r can also have the possibility that is less than small r. Okay. But if it is less than small r, so it basically means that our this entire system is inside the you can say shell. Okay, let me put it here. So we have our option A, and option A means for finite value of small r which can be also less than capital R, where r is the radius of the shell. Therefore we can say that our point O prime will be inside the shell. Point O prime, which you can say represents the position of the center of the dipole. So point O prime will be inside the shell. Inside the shell. But electric field inside the shell is equal to 0. Electric field in the shell will be equal to 0. So because of this, the torque will be equal to 0, or from here we can say if torque is 0, no oscillations. no oscillations. And so it means option A is incorrect. Option A is incorrect. And option B is just reverse of that. Option B categorically states that this value of small r is greater than capital R. Okay. And obviously in this case the electric field will not be equal to 0. So once again this torque will not be equal to 0 and we are going to get simple harmonic motion. So option B is correct. B is correct. So option A is incorrect, option B is correct. Next it says that we have to find out the angular frequency at small r is equal to 2r and small r is equal to 10r. So we already know the formula. So we can say option C. Option C tells us that small r is equal to 2r, and angular frequency expression we already know that omega is equal to, we have this as okay, we have to prove it. So we have to prove it that r is equal to 2r and the angular frequency will be given as 2 sigma p naught divided by epsilon naught multiplied by I. So we simply substitute value of r is equal to 2r. We get that omega square is equal to p naught r square sigma divided by epsilon naught I, and now it becomes 2r whole square, which gives us p naught r square sigma, and this comes as 4 epsilon I and r square. R square cancels out, so we get from here that our omega is equal to p naught epsilon and 2, we can, anyways let us keep inside 4 epsilon naught I and its whole square. Okay, so obviously this is not the given angular frequency option, so option C is incorrect. C is incorrect. Now we come to the option D. Option D states that when small r is equal to 10r, we should be getting our angular frequency is equal to sigma p naught, and this comes as 100 epsilon naught multiplied by r I and its square root. So similarly, we are going to find out our omega square by plugging in r is equal to 10r. So we get omega square is equal to this, we have p naught r square sigma rho r square sigma, and we have this as E naught I, and this comes as our 10r whole square. So we get p naught r square, and this will be 100 r square epsilon naught multiplied by I. Here r square and r square cancels out, so we get that our angular frequency omega is equal to our p naught sigma 100 epsilon naught times I and its square root, which is the required option. So option D is correct. Option D is So C is incorrect and D is correct. Next question. We are given a charge is kept at the central point P of a cylindrical region. Two edges subtend a half angle theta at P as shown in the figure. When theta is equal to 30 degree, then the electric flux through the curved surface of cylinder is phi. If theta is equal to 60 degree, then the electric flux through the curved surface becomes phi upon square root of n. Then the value of n is. The basic figure is given to us. So we have a cylindrical region, and at point P, both top as well as bottom. So let me complete this part also. Okay. Both top and bottom are subtending a half angle of theta at the center. Okay. And we have to find out, basically flux we have to find out and make a comparison. So in this case, we can just make use of the solid angle, and this is, the shape is something like a cone. Okay. This is a shape is like a cone. Okay, and the bottom side it will be also like a conical shape. So you can say that and we have to remember that the flux is being asked with respect to the curved surface. Okay, but the solid angle is with respect to the surfaces of the top as well as bottom. So one is the bottom surface and other one is the top surface, but flux that is being asked is with respect to these curved surfaces. Okay, so we have to keep that in mind. And so let's start with the solid angle. So we can say solid angle of a cone solid angle of a cone of half angle theta, and we can write omega is equal to 2 pi 1 minus cos of theta. Okay. But the angle is being subtended by both the planes, okay, top as well as the bottom. Therefore, we can write that solid angle subtended by both planes. Let us call this as omega t, and that will be also 2 multiplied by 2 pi 1 minus cos of theta. So we can write this as solid angle T will be equal to over 4 pi 1 minus cos of theta. Okay. But we have to find out, because the flux is to be associated with the curved surface. Okay. So we are going to find out the total solid angle that is subtended by the curved surface. So you can say that total solid angle about the point P and that solid angle will be equal to over 4 pi. Therefore, the solid angle because of the curved surface. Solid angle subtended by curved surface. By the curved surface, and let us call this as solid angle curved will be equal to 4 pi minus solid angle total T. So we substitute the value, we get solid angle curved will be equal to 4 pi, we substitute the value, we get this as 4 pi 1 minus cos of theta. So we open the bracket, obviously 4 pi cancels out, so we get this as 4 pi cos of theta. So this is the solid angle because of the curved. Now we are going to find out the flux through the curved surface. Flux through the curved surface, and let us call this as phi curved, which will be equal to our q upon epsilon naught multiplied by our, you can say, solid angle curved and divided by total angle. Solid angle curved we already know, so we get this as q epsilon naught, and we get this as 4 pi cos of theta divided by 4 pi. 4 pi cancels out, so we get the flux passing through the curved surface will be equal to our q upon epsilon naught cos of theta. Now we have two angles. One angle is said to be our 30 degree, and it says that the flux is given as phi. And when angle is 60 degree, the flux is given by phi upon square root of n. So let us use these two values. So we can say for theta is equal to 30 degree, so therefore we require its cos of 30, which will be equal to square root of 3 divided by 2. Therefore we can write that flux through the curved, let me write this straightforward, the angle will be equal to q upon epsilon naught multiplied by square root of 3 divided by 2, and this is given nothing but our phi. Next angle is given to us as 60, so we can say for theta is equal to 60, so we get cos of 60 is equal to our 1 by 2, and we can write that our phi of 60 is equal to q upon epsilon naught multiplied by 1 by 2, and this is given as phi upon square root of 2, square root of n, square root of n. And if we see that this particular thing is equal to our phi divided by root 3. Okay, let me write it here. We can say that our q 2 epsilon naught is equal to phi divided by root 3. So we substitute it here, we get this as phi divided by root 3 is equal to phi upon square root of n. So our n is equal to 3. So value of n is our 3. Next question. It states that an infinite long thin wire having a uniform charge density per unit length of 5 nanocoulomb per meter is passing through a spherical shell of radius 1 meter as shown in the figure. A 10 nanocoulomb charge is distributed uniformly over the spherical shell. If the configuration of the charges remain static, the magnitude of the potential difference between the point P and R in volts is. So basic figure is given to us. We have a spherical shell and its charge density is given as 5 nanocoulomb per meter. Okay. So this is having a charge density of 5 nanocoulomb per meter, and straight wire, it is having a charge density of 10 nanocoulomb. Because total charge is given as 10 nanocoulomb is distributed over. Sorry, my mistake. I written it. Thin wire is given as a charge density of 5 nanocoulomb per meter, and the spherical shell is having a charge distribution of 10 nanocoulomb along the entire spherical shell. So let us suppose this charge is given as capital Q, and we have 2 points P and R. So P is inside the shell and R is the outside the shell. This is the basic diagram given to us. So we have to find the potential difference between point P and R. So first of all, we are going to find out the potential due to a line charge at point P, a general formula, then we can use it for point P as well as R. So we can say electric potential due to line charge. Electric potential due to a line charge. So we can say, or let us write electric field due to a line charge. Electric field. And if electric field, E will be equal to the charge density lambda divided by 2 pi epsilon naught and multiply by R. From here we can write our electric potential. Electric potential V will be equal to minus electric field multiplied by our at any point that is our x, let us call this a dx. So we can write our V for any point x is equal to minus electric field will be our lambda upon 2 pi epsilon naught x, and this comes as our dx. And from here we can, this comes as minus lambda upon 2 pi epsilon naught. Its integration will be giving us a lambda, natural log of x. Okay. And So we have 2 points P and Q. So we are going to find out the potential difference due to the wire for points P and R. So you can say potential difference due to wire. Due to wire. So we can write this as for point P because of wire minus for point R because of the wire. And the distance is over 2 and 0.5. So we can write this as minus lambda 2 pi epsilon naught, and this comes as natural log of 0.5 minus natural log of 2. We multiply by minus. We can write this will be equal to over lambda upon 2 pi epsilon naught, and this comes as natural log of 2 divided by 0.5, and this can be written as lambda upon 2 pi epsilon naught. This comes as natural log of 4. Okay, and values is given to us, we substitute it, and we can say that lambda is our 5 into 10 raised to power minus 9, and 1 second, yeah, and 2 pi epsilon naught will be coming as 18 into 10 raised to power 9. Natural log of 4 is our 1.386. So this will be giving us approximately equal to 124.74 volts, or we can assume this is equal to 125 volts. But this is only because of the wire. Now we are going to find out because of the spherical shell. You can say electric potential due to spherical shell. Electric potential due to spherical shell. Now in this case, the 2 points, one is inside and other is outside. So we can say inside the shell, that is for point P, we can write this as Vp shell will be equal to 1 upon 4 pi epsilon naught, and this comes as Q upon R. And for Q is our outside the shell, that is point R, it is equal to VR for the shell will be equal to 1 upon 4 pi epsilon naught Q upon small r. Now we have to find out the potential difference. Therefore, we can write that Vp for the shell minus Vr for the shell is equal to, we can take Q upon 4 pi epsilon naught common, So inside we are left with 1 upon r minus 1 upon small r. Okay. And radius is our 2 and radius is 1 and other distance is 2. Okay. So therefore we can, this will be coming equal to our 4 pi is our 9 into 10 raised to power 9, 10 into 10 raised to power minus 9, and this comes as 1 minus 1 by 2. The r is the radius and this small r is the distance between the point r and the center. Okay, so this and this goes away, so this comes as 90. 90 divided by 2 will be over 45, so this will be coming as 45 volts. So we found out the individual potential difference because of the wire as well as the shell. Now we find out the total potential difference. Total potential difference, which basically means Vp minus Vr. Okay. And that will be equal to our, because of the wire for both the points, minus because of the shell. We simply substitute the value and we get this as, plus, and we get this as 125 plus 45, giving us 170 volts. So potential difference is 170. Next question. Okay, so we already did our advanced questions. So now we are going to solve the remaining our, you can say, one second. Yes. So this is 2024 main part, and it states that at the center of half ring of radius r, that is 10 centimeter, and a linear charge density of 4 nanocoulomb per meter, the potential difference is x pi v. Then the value of x is, okay, so we are given a half ring of radius r, and the linear charge density is also given to us. Okay, so we can just draw an approximate figure. So we are given a half ring. Suppose this is center O and its radius is given as r, and its linear charge density is given as 4 nanocoulomb per meter, and the potential at center is given to us as x pi v. We have to find out the value of x. So we can write the formula for the potential at the center because of the half ring. Potential at the center of half ring, let us put that is given as V, which will be equal to K and lambda, that is just charge density, multiply by length of the arc and divide by radius r. And this length of arc is nothing but our half length of the ring. So you can say that our length of arc is equal to length of arc for half ring. And let us suppose we represent it by L, capital L rather. So that will be equal to pi multiplied by R. So we get our potential V will be equal to K, and this comes as lambda multiplied by pi R divided by R. R and R cancel out. So we get this will be equal to our, let me put value of, this is our 4 pi epsilon naught and lambda multiplied by pi, and pi also cancel out. So this comes as lambda upon 4 epsilon naught. And we have to write it in the formation of, let's not cancel it, otherwise we won't be able to sort it out. So we can write this will be equal to our K pi lambda. Okay. Value of K we already know, and one second, it is given the x pi V. Okay. And lambda we just substitute with respect to the charge. So we can say that our 4 nanocoulomb. Okay. So this will be equal to K is our 9 into 10 to the power 9, and this comes as 4 into 10 to the power minus and multiply by pi. So here 10 to the power 9, 10 to the power minus 9 cancel out. So we get our V is equal to 36 times pi, and this in volts. But we are given that we are having this as pi times x volts. So therefore we can say that value of x is equal to 36. So value of x is our 36. Next question. We are given that 5 charges plus q plus 5q minus 2q plus 3q and minus 4q are situated as shown in the figure. The electric flux due to this configuration through the surface S is. So basically we are going to use Gauss law, and Gauss law states that charge enclosed, flux is equal to charge enclosed divided by the epsilon naught. You can say Gauss law flux will be equal to, we have this charge enclosed divided by epsilon naught, and here charge enclosed will be our algebraic sum of all the charges. So we can say this will be equal to plus 5q plus q and minus 2q. Here this minus 4q and plus 3q are outside the Gaussian surface, which is given by this part, and divided by epsilon naught. So this gives us as 4q plus and divided by epsilon naught. Therefore option 2 is correct. Next question. It states that the electric field E is given at 2x I unit vector Newton per Coulomb exists in the space. A cube of side 2 meter is placed in the space as per figure given below. The electric flux through the cube is. Okay, so we have to find out the electric flux that is being generated by the electric field, which is governed by this equation 2x times I unit vector. I unit vector means it is towards the positive x-axis. That's the only significance of our electric field. Okay. So our, we can say, net flux will be equal to flux on the, because electric field is from our left to right. Okay. So first of all we are going to find out the flux that will be associated with our this left surface and flux associated with the right surface, and then we are going to algebraically add those fluxes and get the net flux. And we know the relationship between the flux as well as electric field, which is our electric field, our for and A. So we can say, and here area is the area of the face and it is a cube. So we can say that our area of each face, area of each face will be equal to our 4 meter square. Let's find out using the given relationship the electric field on the left as well as on the right face. We can say electric field on each face so first we'll start with our left face. For left face the value of x is our 2. So we get our electric field on the left face will be equal to 2x, and that comes as 2 into 2 is equal to 4 Newton per Coulomb. Similarly, we can find the electric field on the right face. Here value of x is equal to 4. And we can say electric field on the right will be coming as 4 multiplied by 2, giving us 8 Newton per Coulomb. Now we can find out the electric flux through each face. And here on the left face the electric field will be entering the our face, and on the right face it is going to leave the face. Okay, so this is going to help to decide the you can say area vector, sorry. And so we can say flux through each face. Flux through each face first we comes to left face, so we can say it is inward normal along minus I. So we get our flux left is equal to our electric field, and we have here minus of I unit vector and the area. So this comes as minus of 4 and area is of 4, giving us minus 16, and this we have Newton meter square per coulomb. Similarly, we can find out for the right face, and that is our outward normal along positive I. Outward normal along positive I vector. Therefore, we can say our flux right will be equal to our electric field dot positive I vector multiplied by A, and this comes as our 8 multiplied by 4, giving us 32 Newton meter square per coulomb. Now we can easily find out the net flux, which is our algebraic sum. Net flux, let us call this phi net, will be equal to phi for the right plus phi for the left. Right is our 32, left is a minus 16, so this comes as 16 Newton meter square per coulomb. Okay, so answer is 16. Next question. It says that two identical capacitors having same capacitance C, one of them is charged to a potential V and other to the potential 2V. The negative ends of both are connected together. When the positive ends are also connected or joined together, the decrease in energy of the combined system is. So here we are given that we are having two capacitors, identical rather. So let us say we are having two capacitors. These are the two identical capacitors. They are having same capacitance C, and let us call this as C1, and this we call this as C2, and the potential it is charged to V, and the second one is charged to 2V, and it says that negative ends of both are connected together. So suppose this is the negative end, and for the other this is negative end. So first we have connected these two negative ends, and in the second part these positive ends, suppose this is the positive end, they are also connected. Okay. And we have to remember that unless until the charge flow is going to take place only under one condition, that the circuit has to be completed. Okay. So once we have connected the positive end also, the entire circuit will be completed, then only the decrease in energy, or we can say the charge distribution or same potential is going to take place, whatever we can think it. And so let's find out. Suppose the energy of C1 is given as U1, and for this C2 let us suppose this is given as U2. Okay, let me write it otherwise, because it is going to have two parts. One is without connection and other one will be with connection. So with connection, without connection, let us call this as initial. So you can say initial energy so we have for C1, let us call this as our U1 will be equal to over half C1 V square. C1 is C, so we get our U1 is equal to half C V square. Similarly, we can write for C2 that will be over V2, U2 rather, and we have half, and let us call this as C2, and the voltage is given as twice V and whole square. So we can say that our U2 will be equal to this come as twice C V square. So total initial energy. Total initial energy, let us call this as UI, will be equal to U1 plus U2. So we get our initial energy UI will be equal to, we have this as half CV square plus twice CV square. So this comes as 4 plus 1 is 5, giving us 5 by 2 CV square. Now we come to the final configuration. It means when the connection is being made. Final configuration, which is basically after connection. And we are given that the connection means positive is connected to positive and negative is connected to negative. Okay. And the charge it will be redistributed, and the both capacitor is going to reach same voltage. Let us call that as VF, same final voltage. You can say that charge redistributes and both capacitors reach same final voltage. Let us call this as VF. So total charge, or we can say by conservation of charge, we can write that for C1 initial charge, let's suppose that Q1 will be equal to C multiplied by V, and for C2 total charge, let us suppose that is Q2 will be equal to C multiplied by 2V. So total initial charge will be equal to 3 CV. total initial charge, let us call this as Qi, will be equal to Q1 plus Q2, which gives us that Qi will be equal to Cv plus twice Cv, giving us 3 Cv. And using charge conservation, you can say charge conservation, our final charge will be equal to our initial charge, which is our 3 Cv. And we can find out our equivalent capacitance. C equivalent will be equal to C plus C is equal to twice C. So based on this, we can say our final voltage, which we have named as Vf. So we can say final voltage which is our Vf will be equal to final charge upon C equivalent. Final charge is our 3 Cv, equivalent capacitance is twice C, and C and C cancel out, so we get our final voltage is 3 by 2 times V. Now we can easily find out the final energy. We have final energy is our UF will be equal to half C Vf square and half C Vf square, because both the capacitors are same. So we can write this as twice into half capacitance is our C, and Vf we just calculated is our 3 by 2 V whole square. And here this 2 and 2 cancels out, so we get this as 9 by 4 Cv square. So this is our final energy, and we can now easily find out the decrease in energy. Decrease in energy, that is of delta U, will be equal to U initial minus U final. Substitute the values. U initial was our 5 by 2 Cv square minus 9 by 4 Cv square, and 2 with 4 will be LCM, so this becomes 10 minus 9, that is 1 by 4. So we get this half Cv square. So this is the decrease in energy, that is half Cv square. Option 3 is correct. Option 3 is correct. Next question. It says that a parallel plate capacitor with plate separation 5 mm is charged up to by a battery. It is found that introducing a dielectric sheet of thickness 2 mm while keeping the battery connection intact, the capacitor draws 25% more charge from the battery than before. The dielectric constant of the sheet is. So here dielectric is introduced, but battery is kept intact. Battery is not removed. Okay. So it means the supply voltage to the battery is going to remain constant. And it says that the capacitor draws more charge, that is 25% more. Okay. So we can just draw the approximate figure. So we are given that we have a parallel plate capacitor and a battery source is connected to it, and plate separation is 5 millimeter. And okay, so let us suppose the capacitance is given as C and the voltage is our V, supplied voltage. In the second part, it is given that a dielectric is introduced. The thickness of the dielectric is only 2 millimeter. And it is still connected with the battery source, which is our V. And here let us call that charge is our charge volt, and here capacitance we can define later on, that we are interested in charge. So this charge is our charge nu. And we know that when dielectric is introduced, it draws 25% more charge. So we can say that our ratio of new charge old charge will be equal to 1.25. And here we have to remember that the voltage V remains same. Voltage V remains same. And let us assume that a dielectric constant is of K. And if we can say T is the thickness of this dielectric and D is the separation between the plates, then there will be air gap and its thickness will be equal to D minus T. So we can say that thickness of dielectric is T and distance between the plates, distance between the plates is our D. So we can write the thickness of the air gap will be equal to D minus T. So here you can clearly see that we are going to get two capacitors. One is having where air is our dielectric constant whose value is our 1, and other one because of the, you can say, dielectric. So let me redraw the figure here. So we are going to have two capacitors. One is with a dielectric. For the sake of, let us suppose we call this as K2, which will be equal to K, and this is our K1, its value is equal to 1. So this gap is our D minus T, and we have a thickness of T, and this entire distance is our D. So we call this as C1 and we call this as C2. Therefore we can say that capacitor 1 capacitor 1, that is our air, and its dielectric is 1. Therefore, we can write that our C1 will be equal to area is same. So we get our epsilon naught A upon D minus T. Similarly, we can write capacitor 2 which is of dielectric, and K2 given as taken as K rather. So we can write that our C2 will be equal to epsilon naught A divided by thickness is T and multiply by K2, which is nothing but our K. So we get epsilon naught A divided by T multiplied by K. Now we can find out the total capacitance. Total capacitance, let us call this as C nu. We can say 1 upon C nu is equal to 1 upon C1 plus 1 upon C2. So we substitute the values. We get this as epsilon naught A, and this comes as D minus T plus K epsilon naught A, and this comes as T. So we can just take it common. We get this as 1 upon epsilon naught A, and this comes as our D minus T plus T upon K. And capacitance without dielectric, capacitance without dielectric, let us call this C old, and this C old will be equal to epsilon naught A divided by D. So we can just take the ratio. So we get our C nu upon C old. C nu is our 1 upon epsilon naught A, and this comes as D minus T plus T upon K, and this is epsilon naught A upon D. And one second, sorry, it is 1 upon let me write it correctly, because I have calculated this is a 1 upon C nu. So we get this as C old will be our epsilon naught A, and C nu will be equal to epsilon naught A divided by D minus T plus T upon K. That's correct. Epsilon naught T, this cancels out. So we get this is equal to D upon d minus t plus t upon k. And with respect to the charge we are given, so we can easily see our C new, because voltage will be same, upon C old will be equal to charge new upon charge old, because voltage is same, which gives us 1.25. And we can just substitute it. We get this as 1.25 is equal to d upon d minus t plus t upon k. We substitute the value. D is our 5 and t is our 2. So this comes as, sorry, t is our, I think, 2 or 3. 2. So we get this as 3 plus 2 upon k, and from here we can write this as 3 plus 2 upon k is equal to 5 upon 1.25, and 1.25 will be equal to our 4. So we get 2k, 2 upon k, is equal to 4 minus 3, that will be equal to 1, and we get that value of k is equal to 2. So dielectric constant is equal to 2. Dielectric constant of sheet is 2. Next question. We are given that force between 2 point charges 1q and 2q placed in vacuum at r centimeter apart is F. Force between them when placed in a medium having a dielectric K as 5 is r by 5 centimeter apart will be. So we are given 2 charges and they are in vacuum. So we can say force in a vacuum, that is our F is equal to K, charges are Q multiplied by 2Q divided by R square. And in medium, so you can say force in medium, let us suppose that is F prime. We get this as K, sorry, let me not write it K, let me put the 1 upon 4 pi epsilon naught, because K is a dielectric. So this comes as 1 upon 4 pi epsilon naught multiplied by 1 by K, and charge becomes Q multiplied by 2Q. Distance is given now as R by 5 and its whole square. So we can just reformulate this equation. So we get our F prime will be equal to, this comes as 25 upon K is equal to 1 upon 4 pi epsilon naught. This is Q multiplied by 2Q upon R square, and this entire is our F. So we get this will be equal to 25 upon K multiplied by F, and value of K is given as 5. So we can write this as our F prime will be equal to 25 divided by 5 and F. 20 goes by 5. So we get our F prime, that's a force in the medium, is equal to 5 times F. So that comes as 5 times F. Next question. We are given a capacitor of capacitance C and potential V has energy E. It is connected to another capacitor of capacitance 2C and potential 2V. Then the loss of energy is Xe divided by 3. The value of X is. So here we are given two capacitors. Energy is given as E, capacitance is C and potential is V. And we have a second capacitor whose capacitance is 2C, potential is 2V. Okay. And here we are given the loss of energy. So we can just easily find out that, let us call this as, okay, so this can be divided into two parts. First will be initial, that is without connection, and then it will be with connection. So let us call this as initial energies. Initial energies, or we can say without connection. And for that, let us call this as C1 capacitor and this is C2 capacitor. So we can say for C1, initial energy is our U1, which will be equal to our half CV square, and it is given as E. For C2, it is our, and let us suppose that is we call that as E1. No, that is UV. Otherwise it will be confusing. And for C2, let us call that a U2 will be equal to our half 2C, and this is 2V whole square. And 2 and 2 cancel out, so this comes as 4CV square. And therefore we can say total initial energy so we can say total initial energy U will be equal to over U1 plus U2, and U1 is our E, so we can say our U is equal to E plus 4 CV square. And here we can just find out the value of CV square, because half CV square is given as E. So from here we can say our CV square is equal to twice E. So we substitute here, we get this is E plus 4 times CV square, that is comes as twice E, giving us 9 times E. Now after, and let us find out the respective charges also, because conservation of charge we can use. So we can say charge on C1, that is our Q1 will be equal to C times V, and we have charge on C2, Let us call this as Q2, which will be equal to twice C multiplied by twice V, giving us 4 CV. So total initial charge. Total initial charge, let us call that as Qi, will be equal to Q1 plus Q2. So we get an initial charge, that is Qi will be equal to CV plus 4CV, giving us 5 CV. And now we come to the after connection, or we can say final. Final configuration, which is with connection. And charge will be conserved, so we can say initial charge is equal to final charge. Initial charge is equal to final charge, so which means final charge, that is QF, will be equal to 5 CV. And total capacitance, let us call this as C equivalent, will be equal to C1 plus C2, giving us C plus 2C is equal to 3C. So we can find out common final voltage, because once they are connected, they are going to you can attain a common final potential. So we can say common final voltage. Let us call this as VF, that will be equal to our Q final divided by C equivalent. Q final is a 5 CV, and here we have 3C. C and C goes away, so this we get 5 by 3 times V. Now we can find out the final energy. Let us call that a UF, will be equal to half capacitance is our C equivalent and V final square, half 3C, and we have 5 by 3 V square, and this comes as 25 by 9, that is 25 by 3, and 3 to 6. Okay, and so we get our U final will be equal to, this is our 25 by 9 and 75 divided by 18 CV square, and CV square we already know is our 2E, so we substitute it, we get this as 75 upon 18 multiplied by twice E, and this can be written as 25 by 3 times E. Now we can find out energy loss. Energy loss will be equal to U initial minus U final, which gives us 9E minus 25.3 times E, and this gives us as 27, and it will be coming as 2 by 3 times E, but this is given the question at xe upon 3, which gives us that value of x is equal to 2. So value of x is equal to 2. Next question. It states that two identical charged spheres are suspended by a string of equal length. The string makes an angle of 37 with each other. When suspended in liquid of density 0.7 gram per centimeter cube, the angle remains constant. If the density of the material of the sphere is 1.6, the dielectric constant of the liquid is. So here we are given that our angle is going to remain same. Okay, so we can just draw an approximate figure. Suppose this is the main position, and we have two identical charges, same charges. Obviously there will be a force of repulsion between them, and string makes an angle with each other. Okay, so angle is given with each other is 37 degree, and mg will be in downward direction, and this is a tension. Similarly to the other side also, we have our mg and we have a tension, and we are given that the angle should be our same. So if angle is to be same, so we can say the ratio of the force of the electric force in the air to the force, and because of the gravity, that its weight will be equal to force of electric in the liquid divided by force of the gravity in the liquid. So we can write it. We can say that angle remains same. So if angle is same, so we can say F electric, that is electrostatic in air, divided by F gravity, that its weight in air, should be equal to F electric, which is in liquid, divided by F gravity, which is also in the liquid. So let's find out forces within the medium. So first will be our electrostatic force, and that is in air. You can see in air we have electrostatic force, let us call this as Fe, in air will be equal to 1 upon 4 pi epsilon naught q square upon radius square, and we have the gravitational force, which is our Fg in air will be equal to our mg, and we can find out now similarly in the liquid. So So we can see in liquid we can write our F electrostatic in the liquid will be equal to 1 upon K multiplied by 1 upon 4 pi epsilon naught, and we have this as Q square upon R square. And we have to remember this gravitational force is the representation of the effective weight. So in liquid we are not going to write the gravitational force, but we are going to write it as effective weight. So we can say effective weight, which will be nothing but the gravity minus buoyancy. Therefore we can write our Fg in liquid will be equal to our mg minus volume density of the liquid multiplied by g. And m we already know is the mass of the sphere, so we can just substitute and we get this as g. We can take common along with our volume, so we get here density of the sphere minus density of the liquid. So this is a Fg liquid. Now we are going to put the ratio expression. That for this is, let us put equation 1. So we can say from equation 1 we can write this will be equal to our Q square divided by 4 pi epsilon naught R square, and we get this as volume sphere density multiplied by G is equal to, and here we get this as Q square 4 pi epsilon naught R square multiplied by K, and here we get this as volume multiplied by G and density of sphere minus density of the liquid, and these terms cancel out entirely. Here V and G and V and G. So we get this as 1 upon sphere 1 upon density of sphere is equal to 1 upon K density of sphere minus density of liquid. Now we can simplify it. Get this as K density of sphere minus density of liquid is equal to density of sphere, and we can take density of sphere towards the left side, and we can write this as K will be equal to density of sphere upon density of sphere minus density of liquid. This will be equal to 1.4 divided by 1.4 minus 0.7, which will be coming as 2. So therefore constant is 2. So here we can clearly see that the angle between the wires string doesn't matter, whatever it angle might be. This angle is given if we want to use the tension function. We can just divide into 2 components and then balance each component, and we can just solve it based on that also. We are going to get the same answer. Next question. It states that the electric current through a wire varies in time I is equal to I naught beta t, where I naught is 20 ampere and beta is 3 ampere per second. The amount of electric charge crossed through the section of the wire in 20 seconds is. So we have to find out the charge. Charge is nothing but integration of the current. So we can say charge, which is suppose Q, is equal to integration of a current dependent equation and time t. Current is going to vary from 0 to maximum, that is our 20. And we can just substitute our I of t, which gives us 0 to 20, and here we have our I naught plus beta times t derivative of dt, and we can just substitute their values. I naught is our 20, beta is our 3t, this comes as dt. So we get this as our 20t plus 3 by 2 t square 0 to 20. We substitute the value, we get this as limits 20 multiplied by 20, and lower we need not because it is 0, so this comes as 2 by 3, and this is 20 whole square. So we get this as our 400 plus this is our 400 divided by 2, that will be 600, giving us 1000 coulombs. So option 2 is the correct one. Option 2 is correct. Next question. We are given the electric field is given as 6I plus 5J plus 3K Newton per coulomb. The electric flux through the surface area of 3I meter square lying in the YZ plane in SI unit is. And we are given that electric field is given to us, that is our E is our 6I plus 5J plus 3K, and we are given a area which lies in YZ plane. So if it is lying in YZ plane, its area vector will be along x-axis, that is I unit vector. Okay. So, or it is given also, doesn't matter. So we are given our area vector is equal to 30 times I, and flux we already know that our flux phi of E is equal to electric field dot area, which gives us 6I plus 5J plus 3K dot 30I. So we are only interested in I into I, which gives us 180. So option 3 is correct. Is correct. Next question, and it states that in the given figure the charge stored in 6 microfarad when points A and B are joined together by connecting a wire is. So here we have to find out the charge stored in the 6 microfarad capacitor when this A and B are connected to the wire. So under steady state condition, both the capacitors are going to behave as an open circuit. So we can just draw the equivalent of them, and the circuit will be coming like this now. So the capacitors are open circuit, and we have given us this 9 volt. Let us put this is of R1 6 ohm, this is R2 3 ohm, and we call this as 6 C1, that is about 6 microfarad, and this we call as C2, this is our 3 microfarad. Okay. And this is under steady state condition. Sorry, and A and B are connected to each other. This is A and B. So the current will be flowing something like this, and it is here grounded. So you can see at steady state, capacitor C1 and C2 act as open circuit. Therefore, we can say equivalent resistance of the circuit let us call this as R equivalent, will be equal to R1 plus R2, and that is our 3 plus 6 giving us 9 ohm, and let us suppose the current flowing through here is of I. So we can say current through the circuit I will be equal to supply voltage 9 divided by R equivalent gives us 1 ampere. So we need to find out the charge stored in 6 microfarad capacitor. So for charge stored in 6 microfarad capacitor, we should be able to find out the potential difference across the two ends. And so you can say charge stored in the capacitor and that is our C1 6 microfarad. Let us we call that as Q will be equal to C multiplied by delta V. The delta V is the potential difference. Okay. And potential difference is, let us suppose here it is going to have plus 9 volt, and at this point let us call this as point P and this point as Q. So you can say potential at point P, that is our Vp, will be equal to the supply voltage, that is our plus 9. And potential at Q, let us call that as Vq, and the Vq will be equal to the potential across this R2, and potential across R2 will be equal to 3 multiplied by 1 giving us 3 volt. So here we are going to have this 3 volt. Potential through at point Q is equal to our Vq, which will be equal to potential across our R2, which comes as our 1 multiplied by 3 giving us plus 3 volt. Therefore, delta V will be equal to 9 minus 3, giving us 6 volts. So we get the charge Q. Capacitance is given to us as 6. So this comes as 6 multiplied by 10 to the power minus 6, giving us 36 microcoulomb. So the answer is 36 microcoulomb. I think this completes. Yes. So, but one question I forgot to add here, and that is like this. We have a capacitor, and that capacitor is something like stairs. Okay, so we have a, and this capacitor is having something like this, and the distance is D, and the respective area is A by 3. Okay. So it is a, you can say, stepwise capacitor, stair capacitor, you can see it. Okay. And we are given that area of each stair, area of each stair is given to us as A by 3, and height of each stair is given as D. Height of each stair is given as D, and we have to find out the total capacitance of this particular arrangement. Okay. So here we are going to get 3 capacitors. One will be this one, let us call this as C1. Second one will be this one, let us call this as C2, and the third one will be our this one, let us call this as C3. Okay. But here we have to remember that in the parallel plate capacitor, the opposite plate has to be, you can say, of the same area. So we can just modify it. For the first, we are going to get height of D. For the second, this will be forming an entire capacitor. So this height, distance between the plates will be 2D. And for the third, the distance between the plates will be about 3D. Therefore, we can say that for first capacitance, we can just draw it approximately. So we have this as area A by 3. No doubt the original plate is of this entire, okay, but the area of interest for this particular will be only this part. Okay. So this will be our height, will be our D, or we can say the overlapped area. Okay. And first capacitance, that is C1, will be coming as epsilon naught A by 3 and divided by D. Now we come to the second capacitance. For that also we can draw an approximate figure. So this is our complete plate, and second capacitance is at a height D from the first one. This is our second one. So area is our A by 3, but the total height is our 2D now. Okay, and this will be our overlapped area, that is also our A by 3. So we can write our C2 will be equal to epsilon naught A by 3 divided by 2D. And we come to the third capacitance. And here also, so this will be the reference one plate, and this is our third one. So area will be A by 3, but this height will be coming now 3D. So we can say our C3 will be equal to epsilon naught A by 3 divided by 3D. Net capacitance will be equal to C1 plus C2 plus C3. Equivalent capacitance let us call the C equivalent will equal to C1 plus C2 plus C3. So we can write this as epsilon naught A upon 3D plus epsilon naught A upon 60 plus epsilon naught A upon 90. And we can take epsilon naught A upon D as common. We are left with 1 by 3 plus 1 by 6 plus 1 by 9. 18 will be LCM, so this we get as 6 plus 3 plus 2, that is our 11. So this comes as 11 upon 18 epsilon naught A upon D. This is our equivalent capacitance of the given circuit, given arrangement. So this completes all the questions from the year 2024, mains as well as advanced. So we covered this entire questions in 3 parts. Part 1, part 2 were consisting of only of the mains, and this third part we did the advanced as well as the remaining mains questions. So this completes all the 2024. Thank you.